All right, so we're going to work primarily with just alternating current today. I don't remember exactly how much I covered last time, but we'll do some review. Oh, come on, pen work. Where's my cursor? I can't see my cursor. Ah, this is useful. There we go. All right. So remember, before we had most of the circuits we dealt with were direct current, where our current flow is only in one direction. Actually, conventional current this way, as this is the positive side, with our electrons going the other way. But we also get to deal with a lot of alternating current. This is how we schematic symbol for a basic alternating current source. All right. Let's just make this 10 volts. This be 10 volts AC. All right. And in this case, we can, in a lot of times, we will think of current as flowing conventionally either one way or the other, but really it doesn't matter, because in alternating current, as opposed to direct current, where electrons are only flowing in one direction at a given time, in alternating current, depending on which part of the cycle it's on, we'll have full current flowing in one direction at any given time, and at twice that time it'll be going the opposite direction, back and forth. All right, so why do we do this? What's the point? There's a few advantages to alternating current. On a DC system, we remember that remember Ohm's law. Let's change our color here. And how it relates to power, power loss in DC is P equals I squared R. I've lost my notes. There's the hangout. Okay, I'll get the hang of this one day. Power losses. We can reduce our power loss if we use a higher voltage, because given these two relations here, if our resistance is relatively high, in order to transmit the highest amount of current, we need to increase our voltage. And in effect, that will also raise our current, since they're directly proportional. And we'll have higher current here as well, and a higher power throughput. And going from one DC voltage to a higher DC voltage is a bit trickier. Whereas if we remember with alternating current, we can use a transformer with different winding ratios to end up with a higher voltage. Let's undo that. Let's look at some waveforms. So if you were to take, say we take our probes, we'll probe, get a different color going on here. We'll probe here and here between these 2 points. Actually, we'll just... Alright. And we'll get a plot of amplitude, which is voltage, and time. Call this 0 volts, and this is time. Doesn't really matter what units. On direct current, usually it'll just be a nice and flat line. Because our electrons are only going in one direction. We only have one voltage at any reference point at any given time. Whereas our AC circuit we're actually going to need 2 guys here. Depending on the waveform, let's just say, let's make this a sawtooth wave. In which case our voltage might look like this. Or a common AC waveform is a sine wave. Like that. Or we can even have square waves. It's pretty jagged. Oops, I'll just go between there and 0 volts. Alright, so we're going to be dealing with waves. These are all types of AC current, by the way. All work for AC. Alternating current. And we'll skip the magnetism part. We remember that if you take a... Oops, where's my cursor? Why aren't you working? There we go. If we take a wire and create a coil, oops, and put a current through it, that will end up with a magnetic field. It's actually true of any wire. You'll end up with a magnetic field around the wire. And by putting it into the direction of the magnetic field, which way is north or south, like the north and south poles of a magnet, is determined by which way current is flowing through the wire, which way electrons are flowing. It's not important to know to know to remember which way it's going. Just know that there is a magnetic field we're dealing with. And if we introduce something ferrous, something like iron, into the magnetic field, then it will constrain our field like this. And so if we had two wires, oops, why is this not wanting to cooperate today? If we had two wires parallel to each other, they would have each their own magnetic field. And if current is flowing through the same direction in both of these wires, then the magnetic fields will combine. So on and so forth. And if they are opposite, then quite simply they just repel. So using these principles is basically how an AC generator works, or any generator really. If you take a magnet, oops, make you thicker. There we go. If you have a wire, and let's just hook this up to a galvanometer. There we go. Just say this way, 0 volts. We'll just go plus and minus. And we take our magnet, we run our magnet along the wire. It's pushing electrons, essentially. We'll end up with a deflection in one direction or the other, depending on the polarity of the magnetic field and the direction it's being pulled along across. So this is the basis for motors and generators. Generators where the magnet is on the rotor. You can imagine attached here, and then we have another magnet on this side. Rotating. And then to increase the effect of our magnetic field on our conductor here, we can turn it into a coil. So we end up with more surface area exposed to the magnet. And that'll induce, oops, a current. So if instead, this would be a DC generator, instead we have our an opposite pole here. On this sweep, the North Pole induces a rightward current. Now South Pole will induce a leftward current. So here we'd end up, back and forth, we'd end up with a nice sine wave. And there's our AC generator. Let's look at the waveforms a little closer. Some basic things we need to know, basic terms. Alright. So now this is time, and this is 0 volts, this is positive voltage, this is negative voltage. Oops. Alright, and we'll get our sine wave here. Okay, good enough. Alright, we call the peak here with our reference from 0 volts. From here to here, that distance, is our amplitude. The time from, let's see, the part of the wave that's in the positive cycle, this is the positive alternation, excuse me. And conversely, this is a negative cycle or negative alternation. And the time from a positive half cycle to a full negative half cycle, that's a period, or easier, let's just call it peak to peak. That is one period. As a time. As a distance, this is a wavelength. And we've got nice little mathematical symbols for most of these. For wavelength, it's a lowercase lambda. A period, lowercase t, opposed to time, a lowercase t. Amplitude, we generally use a capital A, will work fine, but alpha works as well. And we can number these parts of our waveform. If this is one period, let's look at this cycle here, this half cycle. Then for our period, we could say this is 0 degrees. Our peak is at 90 degrees. And we meet the origin again at 180 degrees. So on and so forth. 270 and 0 degrees. The cycle starts over. We can also think of this in terms of revolutions. So I like to use tau. We call this 1/2 tau. I put 8 there. Why did I put 8? 1/2 tau. In terms of radians, quarter tau, quarter turn, 3/4 turn. Right, so there's a few ways we can quantify our alternating current waveform here. What we want to do is we want to know how the voltage in this equates to an equivalent DC circuit. You might think it's the average. It's not. It's not far off, but not exactly the average. The average of a sine wave is roughly, let's see, 636. So let's compare it to our DC circuit. I actually made one up here we can go back to. Alright, so we've got a load of given resistance here on both sides. Let's just say they're the same resistance, R equals R. And our current, let's forget about voltage for a second. And let's say we're pushing a current of 1 amp through this circuit. So we can take Ohm's law. My keyboard won't work unless this window has focus. It's really annoying. 1 amp. Right? And we know from Ohm's law that we're wasting current here in the form of heat. So let's say we measure that to be, I don't know, 100 degrees. Given both of these circuits, both the same load, both the same amount of current, and therefore power, because power is dependent on current and resistance. In an AC circuit, we wouldn't end up with quite 100 degrees of heat. We'd actually end up with something around 70, let's see, 70.7. A word about heating effects. All right, that's a disparity. It's pretty easy to figure out that disparity compared to DC. We've got a power factor of 0.707. That's just 70.7 over 100. So the effective value of alternating current, empirically, would be 0.707. times the maximum current. And the reason for this is with waveforms, we have to deal with something called root mean square. Let's go ahead and actually we'll go left here. Let's get, and let's go here. Make sure I've got the right one. I think that should be right. Square root 2. Let's have a look. Sine wave. A over square root 2. Yep. Right. That's actually not peak to peak. It's just our amplitude. Right. Our RMS value will be different depending on the waveform. But a sine wave is a good approximation. So we'll go and stick to our sine wave example. I missed your question, Greg. And that's actually a good point. I need to cover that still. So we'll go back to our
Zach,
sine wave here. And
can you hear me?
we have periods. So we know that one period is however many seconds. It's inversely proportional to frequency. All right. So if our cycle here, let's say our period is 1 second, that would equate to a frequency of 1 cycle per second, or 1 hertz. Conversely, if it's a half a second, we end up with a frequency of 2 hertz, so on and so forth. With wavelength is related for any wave. It's the velocity of the wave is the wavelength times the frequency. And while we're dealing with this is just a generalization because with transmission lines that we'll touch on, but AC waves, electricity in a vacuum travels the speed of light. Generally, it'll be slower than the speed of light because of losses in the conductor. But we can go and generalize it as the speed of light. So D equals lambda f. And this is true of radio waves as well. So radio waves in a vacuum, its speed of light is wavelength times frequency. It doesn't. It's a little more complex in how it relates with current and voltage. Really, what frequency, higher frequency. Yes, electricity generally, if we ignore losses in the conductor, will be speed of light. I have the audio turned up, so feel free to interject if there's something confusing. So yeah, I heard it
Ooh.
at one point, but that's fine. Yeah, I hear it. All right. So where were we? We were back at root mean square. So what root mean square effectively means, this is the exact definition for a sine wave. But the general definition, as we apply to either voltage or current, is the effective current is essentially the average of the sums of the squares of the instantaneous current. What does that mean? That's a lot of words. We'll look at it in a second. So we have let's go look back at our sine wave here. And to draw this waveform, there's a few ways we can do it. But we have a few devices to make it easier. We use an oscilloscope, which plots points. It samples. What it does is it takes a sample for each point very quickly and records it so that it can graph it out. And so if we were to take our samples there, let's say we take, oh, I don't know, let's just do 4 samples. So we take a sample here, 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 here. And we take all our samples and we say, well, 0 volts here and 0 volts there. And it's whatever V plus is, and it's whatever V minus is. So plus 10, minus 10, whatever. Doesn't really matter. We take that and we add all those values, we square all those values and we add them together. So u squared plus 10 squared plus minus 10 squared, 0, so on and so forth. And then we have 4 samples, so we needed to find the average. There we go. We'd end up with what? 100 plus 100, 200, and then 100 back. And then just square root 10. And if you are into calculus, you'll know that this is not the real answer. It's not even a very close generalization. We'd have to use integrals to be able to get the entire value, integrals and limits. That's not important entirely to understand. But we'll end up with our root mean square value. And so for an alternating current waveform, that is our effective value. Here it is. And let's move on in the notes here. Pull up the calculator here. And so if we have our RMS equation for a sine wave here, we'd find out that plotted against our that was a horrible sine wave. Get on. What is going on? I can't draw. Plotted against our very rough sine wave. If we drew a line at about 70%, that'd be our RMS value. And we get that from just up here, 1 over square root 2. All right, and just like any other wave, let's go back to my nicely drawn one. I like that. And we'll draw a new one. No, too thin. Mm-hmm. Mm-hmm. And mm-hmm. Not a great negative cycle, but oh well. All right, and we'll take our, where's our RMS value? Here it is. It's about there. So our effective voltage or effective current. And if we were to add another voltage source or current wave, voltage wave, current wave, if we were to, instead of plotting just voltage, we'd end up with current as well. Yeah, we'll use you. You see that our current wave will be in phase with our voltage wave. Got that. I. All right. Generally, we'll only be dealing with the voltage wave. That'll be the important part of the waveform. Let's say we were to add another voltage source that was perfectly 90 degrees out of phase. Same amplitude, just delayed. oops, by a quarter of a period. And these are out of phase. I forget what the symbol for phase difference is. I have the feeling it's phi. Yep. Where'd you go? There we go. Then these two waves out of phase will only end up with maximum and minimum values. I'm sorry, my notes are completely disorganized. What am I trying to say? Better example. This will be simpler. If we had two waves 180 degrees out of phase, then the effective voltage would be nothing. They'd cancel each other out. Alright, there you are, and there you are. Positive, yes. Out of phase, yes, yes, wonderful. Inductors. Where was I going with this? Where's the hangout? Any question thus far? I guess what I'm trying to go with this is we have to be careful when we're using things like Ohm's law. Where Ohm's law remains true, where we talk about either the averages for everything, so the average for current, and resistance will generally be constant. There are special cases though. We'll deal with complex impedances. And same thing with power. If we want to find effective power, we need to use only effective current to calculate it, which would be our root mean square value. And let's see. talk a bit about inductors. Actually, I said we'd do capacitors too. I'm not sure how much we've touched on capacitors. All right. Capacitors are basically just two conductors with high surface area with an insulator between them. And if we move some electrons in, oh, I didn't need you. Because of the static electro effect, we'll end up charging the surface of our insulator with electrons, which we can drain later. This is generally true of ceramic capacitors. When we get pretty low value capacitance, we measure capacitance in farads. Named for Michael Faraday. That's all right. And its basic function is just to store an electric charge. How much of a charge is related, green, by voltage and the total charge of the plate. Where's it going with this? Most higher value capacitors, instead of using a ceramic insulator, they use a dielectric or an electrolyte. Excuse me, an electrolyte is the correct term. They generally look like little cans, like that, and they'll have leads at the bottom. And they're basically two plates, one of them metal and one of a metal oxide, and in between them an insulator, usually paper. And they're all rolled up and dipped in an electrolyte of some sort. And it looks like no one else is watching, so Josh and Greg, if you want to unmute your microphones.
Huh?
I'll field more specific things than this. I did want to get to... You understand capacitors, yes?
It's like a really quick battery that's always reusable.
Sure, okay, good. And you understand inductors from last time, maybe?
Yeah.
Alright. Inductors also store a charge, but they do it... Actually, charge is the wrong word. They store
No, they
energy.
store a magnetic field of voltage.
Correct. All right. So, what I wanted to get to today was tank circuits. Tank circuits are pretty simple. It's just a capacitor and inductor, either in series or parallel, doesn't matter.
Series and parallel.
And once you've added energy to this circuit, it'll slosh between the inductor and the capacitor, back and forth. And there's a lovely equation relating this. 1 over, is it tau square root LC? Actually, it comes from angular velocity is 1 over square root LC.
Wait, so this will oscillate?
Yeah, basically, if there are no losses in this circuit, it'll slosh back and forth for forever.
Yeah, but since your circuit's made out of copper and not some sort of gravitational singularity magnet, it will eventually run out.
Mm-hmm. Well, this is basically resonant frequency.
Actually,
Whatever.
I wonder if there's a way to make it go forever with superfluids.
You mean superconductors?
No superfluids. Remember I showed you once that fountain that would run forever as long as it was cold?
Right.
Yeah, I wonder if there's some sort of similar bullshit here.
I don't know. Actually, maybe with a superconductor. Yeah, because a superconductor is just really cold. Yeah, I'm sure
Yeah,
you.
but for to work with a superconductor, it'd have to be at actually absolute zero, whereas with superfluid, those do weird shit at like 2 Kelvin.
Mm, I don't know. That'd be an interesting experiment.
Notice the chat. Josh says hi.
Hi, Josh. Yeah, I've seen it. I have to keep remembering. Are LC circuits used in analog synthesizers? Not really. Uh, the frequencies are so low that given this relationship here, basically, uh, 1 over square root LC, you'd have to have. Let me make sure I get this right. You'd have to have, for a low, relatively low frequency, so let's say 400 hertz. One over square root LC. This would have to be fairly large values. Correct. Let me make sure. Yeah, I'm right. You'd have to have really large values of L or C. So because large value capacitors are expensive to make, and because large value inductors are huge, I mean, I can show you a number of capacitors here. The biggest one I have, let me see if I can switch on video. UVC camera, yep, that's it. One camera, go on. It doesn't want to do it. Why not? Oh, I thought this would be easier. Oh, wait, could you see my video just a moment ago? No. Okay, we'll do it the hacky way. Come on. You want to? There we go. Right, these are the most physically large capacitors I have, and it's 1500 microfarads. So for audio level frequencies, you're going to end up with really large values. Now, what we can do for analog sense for audio synthesizers, we do something similar. Where's the point? Instead of using capacitance and come on. Instead of an LC circuit, we deal with RC circuits. So it could be a capacitor. Let's make you red. Capacitor and resistor in parallel. And it doesn't exactly slosh back and forth, so you have to keep adding energy. But the resistor, usually a resistor there and a resistor here, resistor here controls the rate at which the capacitor charges. And then generally, once the capacitor is saturated, you'll trigger the you'll stop adding energy, usually with a transistor. So there'll be a transistor junction here, and once this capacitor is charged enough to turn on the transistor, it'll turn off adding energy, and it will discharge through this resistor. So you can control the rate at which the capacitor charges and discharges, and you can end up with audio frequencies like that. Generally pretty regular. There's an integrated circuit called the 555 timer, which is pretty ubiquitous. Basically, it's the chip has a few pins on it where you put in RC networks, resistance capacitance networks. And the RC network defines the timing for the output of the 555 timer. It's really, you can do this in discrete components. It involves a few comparators and op-amps. And let's go ahead and go into touch on comparators. Comparator, actually an op-amp. We need to know what an op-amp is. It's basically an amplifier. All right. So an op-amp always has two different inputs and an output. This is the non-inverting output. And this is the inverting input and output. And these will generally have a gain, all right? So if you were to put a signal in here, then you'd get the full gain worth out, which is generally very large for operational amplifiers. It's usually something like 23. gain. Gain is unitless. You can express it as decibels. I'm not sure what that'd be as decibels. So to control that, we can offer some feedback. We take the output and we feed back some of the output signal into the inverting input, and then those waves combine. So we end up with, if our input signal looked like this, our output signal would be exactly the same but higher amplitude. And if we fed back some of that output negatively, because the op-amp inverts it, then you'd end up with a lower amplitude output. These are very important in advanced electronics. They pop up everywhere. There's also, yeah, operational amplifier. What's going on in the op-amp? Well, let's look at a, yeah, here's a good one. It's got a few stages. I'll just draw this out. It's an op-amp can be made from discrete components. We have red back. Generally, we'll have that's an NPN transistor. It's supposed to be. This is way too much to draw. I'm going to find the schematic. How am I going to do that? Oh. Wikipedia. Go! Engage. Oh, come on, browser. Here we go. This is what I wanted. Hello. Op-amp load. I don't know. Oh, no, I do know. They were used in analog computers. So they performed operations. That's why they're called operational amplifiers. Does that make sense? What is going on here? Come on. All my notes from last time. There we go. Should actually be able to. Ah, blimey. Well, while we're waiting for that to load, it's basically, it has a differential stage, so it'll be two transistors. It'll be two transistors in a differential configuration, which looks like this. Mm. And then you generally have these. Then this is referenced here, and this is ground referenced. I'm sorry, it's not ground referenced. It's a voltage divider with a negative voltage source. And then we'd end up with a... Okay, this is messy, but this is basically it. Oops. Out. And this will be the non-inverting input, this will be the inverting input, and a positive and a negative voltage source. Need an AC current. Signal, just AC voltage. It could be DC voltage, in which case it would be analog adding. It doesn't matter in this case. Sound is an AC signal. Generally, we talk about AC signals. They're usually very, very low voltages. So on the order of less than 3 volts or so. Anywhere from the noise floor will generally be around 1 millivolt, depending on the equipment. I can show you. Let's see. Let's see if our op-amp loaded. Oh no, it didn't. Good time for the server to stop working there. Whatever. I'll show you a tank circuit. This is a nice little signal generator I picked up at the Handfest. Let me set this here. It's a tube-based construction, and it's really, really neat. This is actually really good piece of equipment for illustrating this. I'm going to set up a tank circuit on this breadboard. I'm leaving the Joule Thief we made last time. A tank circuit is just a capacitor and an inductor. I'll use this one. I'm not sure what the value is, and given our equation there, we can use a tank circuit to figure out the value of one of these if the other one is known. So we know the value of the capacitor. It's 47 nano, I think. If it's 47,000 picofarads, it's 47 nanofarads. Yeah, I think that's right. And then an inductor, it actually does have a value printed there. But let's pretend we don't know the value. So I'm going to jack that in there. And I'm just going to connect our signal generator to this circuit. It's AC, so it doesn't matter which one I connect it to. And I'll plug in the oscilloscope here. I'm just probing across the tank circuit. All right, so what was that? Hello? Noise. Oh, hello. What on earth are you? It's not turned on yet. What's going on here? Apparently it's resonant. Just what is going on here? It's resonant just from the whatever's leaking in from somewhere. Probably this microphone or this camera. I don't know. That's really weird.
The cosmic
It shouldn't be doing
microwave
that.
background radiation.
I mean, it is oscillating pretty good, like a megahertz or two. It's just, I'll just blame it on noise. I should be able to turn this on and.
Just noise, Zach? Think about it. There's stuff from the beginning of time going through there.
No, microwave radiation is too high of a frequency. Okay, so there we go.
It's still
See
going
that?
through there,
That
it's
was,
just not detected.
that was the valves warming up. So basically, I've just got an oscillate. Yeah. Okay, Greg. Quick aside. Cosmic microwave background radiation. Microwaves are really high frequency compared to this. we're talking about the range of kilohertz and megahertz, and whereas nothing under 30 megahertz gets through the atmosphere. So all right, so I've got a variable frequency signal generator on our tank circuit here. Make sure it's still intact. Yes. All right, so basically what I want to do is I want to adjust the frequency until we have a maximum magnitude. Let me see. Yeah, that's not going to work. So I'm just going to keep going. I'm going to bring up my measurement here. So let's see. Not enough there. Apparently, let me just double check. Yeah. So this only goes from down to 150 kilocycles. It looks like, let me change bands. .38 millivolts, 38.8, 38.8, 38.4, 39. Still getting bigger. So this must be 32. I think we overshot the frequency a bit. Right, 39. .2. I guess I can call that a maximum. So it's frequency of 882.210 kilohertz. And we can plug it in our equation here. We're trying to find L. We know C is 4.7 times 10 to the minus, minus 8, I think. I'll be right. Let's see. 0.047. Yeah, that's right. How did I do that? Alright. Into the minus 8. And I am too lazy to do this by hand, so I'm going to plug it in my computer algebra system. 882.210 882.210 equals 1 over 2 times pi times L times 4.7 times 10 to the minus 8 to the 1/2 power, and solve for L. It is 0.0026 blah 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 over pi to the squared. What is that in magic, in real things? Real numbers, 0.0 pi divided by, and there we go, 6.9, let's round that up, 7. So L is 7 times 10 to the minus 7. What was that? 0.00000. Let's see, 1, 2, 3, 4, 5. What was that? 7? 1, 2, 3, 4, 5, 6, 7. Yep, 7 henries, which is what? Micro? See, that's micro. I don't remember my SI prefixes. What are my SI prefixes? Metric prefix. Here we go. Micro is right there, so that's 0.7 micro henries. It says it's supposed to be 1,000 millihenries. Millihenries are big. Microhenries. It says it's supposed to be much more than that. So what's going on? Let's try going forward. What's the resonant frequency if it is that many microfarads or microhenries? So that'd be 1 over F equals 1 over pi 2 and then 1 0 0 0. 10 with 2 zeros, but that's microhenries. Ah, these measurement systems are awful. Microhenries. 10 with 2 zeros would get us 0.01. Yeah, 0.01. No. Okay. 0.001. That's 1 microhenry. We have 10 with 2 zeros. 0.001. 0.001 times 4.7 e to the minus 8 multiply square root times and then inverse. That's, oh yeah, that's why. That's 23. The resonance frequency is supposed to be 23.15. Wait, 215 kilohertz. We must be on a harmonic. So let's see, 882, 23.215 goes into it 38 times, almost exactly. So we're on the 38th, harmonic. That's why that didn't work. If my signal generator went down to audio frequencies, that would work. So I guess actually, I guess you can. It's uncommon. You generally don't have LC circuits at audio frequencies. Yeah, that's pretty close. 23 kilohertz. It's almost human hearing range. I'm going to stop the broadcast here.